Today, on our first episode of the ASTRA Talks, we're grateful to be joined by Professor Surhud S. Professor More is an Indian astrophysicist, researcher, and educator. His research specializes in dark matter halos, which are structures made of dark matter that effectively create a halo around galaxies. You will often find Professor More at the Inter-University Center for Astronomy and Astrophysics, or IUCAA in Pune. He is a faculty member at IUCAA and heads the LSST project. He has been awarded the Otto Hahn Medal and the Vigyan Yuva Shanti Swarup Bhatnagar Prize for his excellent work in cosmology over the years. With almost 72,000 citations on Google Scholar, Professor More is not only a prolific researcher but also a master of science communication. I've had the honor to meet Professor More on multiple occasions. In fact, Sir's talk was the first ever I attended on dark matter and dark energy. I'm honored to welcome you to the show, Professor Surhud More.
Hey, thank you. Thank you, Manan.
So let's begin with the questions. Starting with, what is your perspective on dark matter and dark energy? And what is something that you would like our viewers to know about how these forces interact and shape our universe?
Right. So, um, cosmologists have been studying the universe for quite a few decades now, especially with the newest observatories and instrumentation that is available to them. And one of the things, the puzzling things that has come about is that the matter that we are used to, things that we are made up of, or for the physics of which we know, that constitutes a very small portion of the total energy density in the universe. If you look at it, it's only just 5% or so. So the rest 95% is made up of these two components, dark matter and dark energy. Dark matter is something which acts like matter. It has gravitational forces, and it interacts with ordinary matter via gravity. But it does not interact with light, as far as we know. And because it does not interact with light, we cannot see it in the normal way that we can see things which emit light or which reflect light. Um, and so that's dark matter for you. It just behaves like ordinary matter, clumps, and can form structures. On the other hand, dark energy is this mysterious energy which people have been trying to understand since its discovery, but it has been very hard to put a finger on. So, this dark energy was initially introduced because what astronomers found is that the universe is expanding at an accelerated rate. If the universe just had matter, you would have expected that the expansion rate would slow down as a function of time. Just like a stone which is thrown up, if you throw it up and it continues to go up with some velocity, but you will see that its speed, its velocity will decrease as a function of time. So something similar was expected for the expansion rate of the universe as well. But instead, what they found is that the universe is expanding at an accelerated rate. And so this particular behavior is attributed to dark energy. And it is one of the, again, most mysterious components because, especially from the theoretical side, we don't know what exactly it is. Okay. So the dark energy about 70%, dark matter about 25%, and the rest 5% of ordinary matter is what makes up the entirety of the universe. And since a lot of it is what we don't understand, we try to study it, we try to understand the properties of these components, we try to understand whether there may be interactions between them. So far, we have not seen any, but we also try to understand phenomenologically how they behave. Okay. So to work out observationally what these components may be doing.
Absolutely. So, would you like to comment on what scale they work on? So, for example, uh, I believe dark matter, it works on more, it dominates at an intergalactic scale rather than inherently across the universe, and dark energy somewhat works all across the universe. So, would you like to comment on that?
Yeah, so dark matter and dark energy work all throughout. I mean, gravity is a long range force, and so it's not necessarily restricted to small scales. So But as you go further and further out, then if you see a dark matter clump here, then its effects on a dark matter clump which is really far away, then it really the motion within the expanding space that you see is governed by nearby objects that are there. But the overall expansion is governed entirely by dark matter and dark energy that we see. Of course, dark matter also shapes shapes the galaxies that we see and the gas around these galaxies, how it is distributed, the overdensity, so how clumped this dark matter is, that clumpiness does govern how these ordinary matter is distributed around the halo. Yeah. So
Absolutely.
overall, these scales are vast and large, as is the case in all of astronomy.
That is absolutely right. And you mentioned halos, and that is our next question. So, how do galaxies reveal their surrounding dark matter halos, and what do scientists infer from these halos?
Right. So in the 1930s, at that time, people had just started to study some of these galaxies, okay, and try to look at their distances, how far away from us they are, and then also how big these objects are, how fast they are moving. So Fritz Zwicky was one of these scientists, and he uh, did an interesting study. He looked at a galaxy cluster, one of these nearby objects, the Virgo and the Coma clusters. And there you see many hundreds of thousands of galaxies, which are in a very small region of space. And for these many galaxies, what he did is he measured their positions, he knew what their distances to us were. And so he had a rough idea of the size of these galaxy clusters. And then he measured the internal velocities of these galaxies, so how fast they are moving with respect to each other. So when he measured that, he noticed that you can use these velocities in order to measure the mass of the galaxy cluster itself. So you can imagine if you are holding a slingshot, so you have a thread and some stone is tied to it. The faster you pull it, the faster it moves around, right?
Right.
And so just by looking at the velocity and this distance of the string, you can figure out how fast you need to pull. Okay, so similarly, in this case, the velocities of these galaxies, they are determined by the pull, and here it is the gravitational pull of the entire galaxy cluster. And so if the pull is larger, then the velocities are larger. So by looking at the velocities, you can infer what the pull must be. And this mass that he inferred based on the pull, it turned out to be many times larger than the mass he could see with his own eyes. So, mass made up of stars within galaxies which emit light. And so that's where he coined the term dark matter. So, matter which cannot be seen.
Right.
Okay. And so one of the ways that we probe this matter which cannot be seen is via these motions of galaxies. So that's one. That is something that I worked on during my PhD. But then you can also see it through an effect called gravitational lensing, where light coming from really far away galaxies, if it encounters a dark matter halo in between, which has its own galaxies, then the light coming from these background galaxies can get bent. And when it gets bent, then how much it gets bent or how much it gets distorted, that tells you what the mass of this intermediate dark matter clump is. Okay? So that's how we try to learn about dark matter, even though we cannot directly see it. Okay. Um, then once we know these masses, what we can do is we can make a connection between the properties of galaxies and the dark matter that is around them. And what we see is not something very unexpected. If you have a big clump of a dark matter halo, then it also forms a big galaxy. And if you have a smaller clump, then it forms a smaller galaxy. But working this connection out in detail, understanding how this 5% of matter, which then goes into these galaxies and stars, how its distribution is shaped by the distribution of dark matter around in the entirety of the universe, is part of ongoing research, and that's what we try to.
All right, so I think we brushed up on some history about dark matter and how it came to be named, and also what we infer from dark matter halos. We also touched upon gravitational lensing, and I think that was one of the topics that you've actively worked on as well. So I think
Yeah.
that was something that was quite interesting to know. So now let's move on to our next question. You're part of massive international survey projects the Subaru Hyper Supreme Cam and the future LSST project. So, what's a discovery or a moment from work that seemed counterintuitive or surprising?
Right. So there are many times when we are thrown up with surprises in these surveys, right? And some of them are very technical, so it is very hard to at least mention in this kind of a context right now because you try to think that like, well, something should behave in a certain manner, and then you get the results from the data, and you try to see, and it's not making sense, and then you think about it a little bit more, and then you start to piece together why some of these things may be happening. But I think I can tell you about some of the results that have come about with the Subaru Hyper Supreme Cam survey. So, using this technique called gravitational lensing, one of the things that we did is we created a map of dark matter in the universe. Okay. And when we construct this map, we can make actually not a 2D map, but a three-dimensional map of dark matter in the universe. And so think about it as in early times when people used to go around with ships and try to figure out what all are the countries and land masses on the earth. And so now we feel like voyagers in this vast cosmos, where we are trying to figure out where these islands are located, where there is a lot of dark matter and potentially a lot of galaxies out there. Okay, so one of the things that is expected from theoretical predictions is that as the universe grows older and older, you start to see that structure is building up. Okay, so things are less clumpy in the young universe, and as the universe grows older, they become more and more clumpy. And so, with the help of this 3D dark matter map, you can actually visually see it. Okay, so if you see at a slice which is at a larger distance away from us, which means it's a early part of the universe, you can see that the clumpiness is lower. And as you go further and closer and closer to us, which means the universe has grown older and older, then you can see that the clumpiness has increased. So we try to map this out in equations, but rather than in equations, looking at the dark matter map and visualizing it directly is something else. And so we had made this nice movie of a dark matter map, and you can see some of these things there. So that was pretty cool when that happened. Of course, what is going to happen with the survey like Rubin Legacy Survey of Space and Time, which is going to make a movie of roughly half of the sky that is visible from a location point called Chile. And so, um, what this Rubin LSST is going to allow you is to make this map of dark matter over about half of the sky. Okay? So right now we have only a small part, which is about 1/40th of the sky, which we did from the Subaru telescope. There are other maps which are slightly lower resolution but bigger areas. And so what Rubin LSST is going to allow us is to make maps at the same quality as the Subaru Hyper Supreme Cam survey, but over half of the part of the sky. And so you can imagine the kind of research that we can do and the precision that we can achieve, and the uh, the amount by which we can constrain where dark matter is distributed, how it grows, and with this also learn about dark energy.
Absolutely. So scalability is something that is quite important when we are talking about observations that are at such a large cosmic scale.
Yes.
Uh, so you recently received the Vigyan Yuva Bhatnagar Award, and I would like to congratulate you for that. Obviously, you're well
Thank you
deserved.
so much.
Uh, so what is something you would like young people, especially students and aspiring researchers, to take away from your journey in science?
Well, I mean, receiving this prize was, of course, a very humbling moment, especially the auspicious halls of the Ganatantra Mandap where this ceremony is held. But I think, I mean, first of all, um, I need to acknowledge all the support that I have been receiving from all the students and the postdocs, as well as collaborators all over the world who have been working with me. Oftentimes, scientific work gets awarded to one person, but then there is a big community which is actually behind the scientific work that gets published. In addition to that, of course, there are family members who have to put in a lot of effort in order to make sure that I am able to go and do many of the things that I'm able to do. Right?
Yeah.
So that's the first thing. But then after this, if you want to see, I mean, what young researchers should take away or young students should take away, one of the things is you do science by wanting to do it, right? Or maintaining a passion to do science and remaining curious. What has often happened, especially when I've worked with school kids, I've noticed that oftentimes we are being spoon fed some information. And so, if you look at science textbooks, sometimes then there will be facts which are given rather than making us think. And so, I think what is important for students to remember is to take everything that you see. Um, mm, I mean, whatever knowledge you learn, try to always question it. And when you question it, that's when even the teacher learns and even you learn better. And so that's basically the path of science. The other thing that I would like to say is don't be afraid of making mistakes because science itself is full of mistakes. And the only thing that is important is if you make mistakes, you learn from it and then you move forward, right? And find a path forward. So those are the main things that I think I would want your listeners to take away.
Sure, absolutely. I think that's a very great message, and it is coincidentally something that I implemented in a talk that I gave in my own school. So last week I gave a talk on the same matter, dark matter. That's a pun not intended, but dark matter, dark energy, and gravitational lensing. So I was going about with what the universe is and what researchers study, and I also asked people that, okay, what is your thinking process behind this? And when we talk at the end of our discussion, rather, it wasn't a talk exactly, we tried to create a discussion with our students. And in this discussion, we tried to hypothesize what could be some answers to open questions, like for example, is our understanding of gravity flawed? That is one of the big questions that are there out there in the standard model. And
Yes.
why is the sun's corona hotter than the surface? So questions like
Yeah.
these were what we tried to encourage. And uh, I think I really love the passion that students showed, and I also think that it really reflects the spirit that you were trying to bring through the answer of this
Indeed.
question.
Yeah. I think as students learning what are the open questions and then trying to make progress towards understanding why these questions are open, what other people have tried, I think these are all parts of being able to do good science. And I'm glad that you guys are doing it even at school level. So that's very encouraging.
Thank you so much. Following up on that, we are going to move on to a bit of talking about a bit of AI. So,
Hmm.
considering the advent of AI and its really fast progression, what are the top three skills or habits that the best researchers look for students that they take for PhD or postdoc?
Okay. I mean, see, artificial intelligence oftentimes is frowned upon and looked oddly upon, but I think it's a tool like any other tool. And so, what you have to be careful about is to know its limitations and to know what it can do really well. because if you can master artificial intelligence, at least when I say master, it would be in this case, it's basically using AI, right, as tool. Then to understand what its, as I said, what its limitations are, so that you can get the best out of it. Okay. So I remember there definitely was a time when computers were invented, or even before that, calculators were invented, and people said, "Why use this?" And you see that, well, when you use calculators, you are freeing yourself up to do even more creative tasks, right, than what just the number crunching that you used to do, right? And so I think you always have to use the tools that are available to you. And I think the best researchers or students, it won't be someone who is trying to run away from AI or to use just AI, but the people who know how to get the best things out of AI rather than um, either of the extremes that I talked about.
Absolutely. I think the balance is something that we continuously need to maintain in research, and
Indeed.
accuracy is something that we should always keep in our hand. I think
Yeah.
that is very important.
Yeah, I mean, the other problem is it's there are these issues of hallucinations which are present in artificial intelligence. And nowadays, oftentimes, artificial intelligence is being trained on data which is also generated by artificial intelligence. So there's some kind of reinforcement that can happen. And so, if there are wrong concepts that get fed, then wrong concepts also get churned out. And then it becomes a runaway process. And so, understanding these things, where hallucinations may be coming in, where things are reasonable, that becomes, I think, important. The challenge that is going to be there is um, the outputs of AI are easier to generate, and they will come out at a pace that you cannot actually control and be able to fact check all the time, right? And so I think that is the part which AI is going to make. I mean, it's going to become challenging in the age of AI. But things are going to change, and my oftentimes my suggestion to younger people was is always that you try to keep yourself um, um, I mean, at a place where you are able to learn things quickly. Okay. And so, whatever challenges then that come about, then you are able to adapt quickly to these challenges. And so, don't shun away from new things. You have to try to embrace them, but embrace them with caution.
Yeah. So always learning new things is the way to grow.
Yeah.
Uh, Coming to our concluding question, talking about India as a country, we are increasingly taking part in enormous astronomy and aeronautics projects. So, from your perspective, what are the unique strengths of India as a country in global collaboration, and where do you think we need to improve the most?
Yes. I mean, India brings a lot of things into the, I mean, for global collaborations. We have been involved with a number of mega science projects as well. And typically, it's a win win for all sides because what happens is when you have these large international collaborations and large international projects, it is not something that is possible necessarily to be done just by one country because the costs are enormous. And so the workload can be shared easily. So that's the first part. A project like the 30-meter telescope, which India is part of, then it's a collaboration of many different countries. And what happens is it allows countries like India to not only contribute, but also contribute and learn from it. Right. So the technology that is used to build these big telescopes and projects that gets developed also indigenously. And once you have things which are developing indigenously, it helps in building bigger things directly inside the country, right? If you look at projects like LIGO, for example, where we are going to have this big interferometer gravitational wave observatory, which is going to be built in Maharashtra. Then the technology required to do this, it spans many different domains. So whether it's lasers, vacuum technology, mirrors, all of these things, precision equipments that you need to build, right? So um, I think it's a win-win. For LIGO, for example, the geographic advantage that we have. So if you put a third detector directly in the US, so there are two already in the US. If you put a third detector in the US, it is less valuable than putting it in a place which is farther away. And this is because it increases the baseline. So think about these gravitational waves as something that comes from the merging of these black holes. And the way we know where they are coming from is not by making images, but by understanding when the first wave reached one of the detectors and then the next. Okay, so this is basically similar to how our ears detect from where sound is coming. So even if you close your eyes, if the sound is coming from that particular direction, then this ear hears it first and then the next ear. Your brain does not garble it, but it uses this information of when that wave reached one ear compared to the other to figure out in which direction the sound is coming from. And so now, if you move your ears a little bit further apart, then and keep it further apart, then your accuracy of pinpointing things it improves. Plus, having three detectors separated all over the globe, it gives you different information about these gravitational waves. So overall, I think it's basically a lot of win-win situations that are present. In fact, countries get involved in many of these projects by looking at the kind of benefit that we will get, not just by being in the project, but in the long term. Because it's a lot of money that gets invested. And so it cannot be just for only those few scientists who are working for it, but it should benefit the larger growth of the society as well. So I think India has a lot of scope to get into these different collaborations, and when funds are drying up in different places, if many countries pull together, then in the end, astronomy is a science for all of humanity. It's not just for one particular country, and so it also democratizes the entire process. So that's good about good things about these international collaborations that are possible.